right, so let's get started. So I want to thank Blaise Tyne for agreeing to do this presentation today. At very short notice, I might add. The original speaker was called away for NOCS duties. So Blaise is a PhD student working with Professor Kim and Professor Yalamanchili at Georgia Tech, and he's going to talk about single source hardware software co-design. Okay, you can get started, Blaise.
Okay, so good afternoon. Thanks for attending this talk. So I'll be talking about single source hardware software co-design. This work was supervised by Professor Yalamanchili and Professor Yusen Kim at Georgia Tech. The outline for this talk, I will be going through the motivation. I will present what single source hardware software co-design is, and also mention some of the compiler optimization that we had to do during this work. And then I will present the taxonomy of mainstream HDL. So this talk will actually be mainly about the HDL that we implemented. And I will go over some of evaluation and then the conclusion. The motivation for this work, I'd like to start with mentioning that in the space of applications where we have machine learning and graph analytics, algorithms are actually changing in a really fast pace. And this has actually pushed the software industry into adopting some rapid development best practices like Agile and DevOps to really integrate the processes. But most of these changes have not really affected the hardware side. In the context of acceleration specifically, where because applications are changing so fast, the design specification also change. And it is important on the hardware side to also being able to adopt some of these agile, or at least have an opportunity to have much more integration in the tool chain. On the hardware side, we have the Moore's law, which is the challenges that comes with the end of Moore's laws, and the new trend in architecture where hardware specialization is basically becoming the mainstream approach into continuing scaling in computation. And there's also the NOC with hundreds of chips on the same board, that also creates new challenges that on the hardware side this has to be addressed. There was a review from DARPA back in 2017 where they basically found out that the verification cost in hardware development is actually 40% of the entire development cycle. So there is a need to really address the cost of verification, which is somehow also related to the fact that we have so many more components on the SoC and the challenges that comes with heterogeneity and the interconnect complexity. So I want to present here the way in hardware we have looked into how to make the whole co-design or development process efficient. The way hardware development process works currently is that you have different layers of abstraction, starting with the gate level abstraction, which is the lowest. I mean, you could use Verilog to write your entire hardware block at the gate level, but that would be extremely difficult, and you probably get the best quality design, but just the cost is just too high. And RGA has provided a much better abstraction that balances productivity and give you quite an efficient hardware. The other level abstraction right above RGL is cycle level simulation or system simulation in some context where you're talking about system C, for instance, which basically allows you to kind of do some modeling of your design really closely to the software side without having to pay the penalty of investing too much time into the actual hardware RTL. And at the really top level, you have the functional level modeling. At this level, you basically just implement whatever component that you need to implement directly in using the highest abstraction possible, or C++ or Java. Um, and, and this is what the traditional hardware design flow looks like. So you have the application. We start with an application, then you have the hardware and software partitioning stage. And then after that, the next process is generally you do some functional modeling or sometimes some cycle level modeling, and then do verification. These stages is basically taking place, I would say, at the software level. All of these components are directly connected. Like when you do functional verification, you usually use input coming directly from the application. Then right after that, once functional verification passes, we have the stage where you actually do the direct hardware implementation, which happens in RTL, for instance. And in this space, there's also RTL verification, which is a completely separate mechanism that actually uses special test bench. Usually doesn't consume inputs directly from the application, but some form of micro benchmark or micro test tree that is used to feed to the RTL simulator before you get to the synthesis and ASIC, if that's your target. The concept of single source hardware software co-design actually it's not completely new. The concept of single source actually exists already in heterogeneous programming with applications like APIs like CUDA, OpenNP, OpenACC, CCL. And the advantage of bringing the GPU programming together with the application, you basically have the ease of using a single language for your entire application space. You have a uniform development methodology, and also the tools is basically the same. You have the ability of sharing resources between the host and the accelerator, like configuration files, sharing data structures, and so on, libraries. The cost of verification is greatly reduced just because of that integration. And then also, CUDA can integrate very easily with HPC applications that are C++ based. So you have also the integration with the rest of the ecosystem out there. Our approach for single source hardware and software co-design is basically about moving RTL modeling all back to into the software space as well, so that the only thing that remains is hardware is just what is needed to do the synthesis to FPGA or ASIC. And the gain with this approach is that you have integrated co-design, software and hardware design flow are basically mixed. You have the co-verification support where you have software and hardware can be verified at the same time. You can directly use input directly from the application. You don't need to have a dedicated test bench. It also allows you to merge the level of abstraction at the same layer. And then because the languages and tools are basically shared, you basically have a much lower cost development process. The single source development methodology that we have in our cache framework is basically as the following. So during the design specification, you may have data structure that are shared with the hardware and the application and config file, simply because they basically belong to the same domain, they use the same language. You have the ability, if you do some functional modeling, your implementation of the functional model of your component will also be done using the same tool and then the same language. And you will have ability to directly debug it using the application, the application inputs. If you decide to implement cycle level modeling, again, you will have exactly the same consistent experience of using the same tool set, the same framework, and the ability to even do design space exploration. If you move to the next layer of abstraction where you decide to optimize the design to RTL, you will also be benefiting exactly the same abstraction. There's the same tool set, the same language, and the integrated simulation and also the debugging. The next thing that we also support is the ability to prototype the design, where you can mix your RTL with HLS so that you can actually run it on FPGA. Another aspect of this stage is also scenarios where you want to optimize a specific HLS kernel and have an optimized RTL library inside. This is what our framework architecture, system architecture looks like. So we have a DSL which is basically what is powering the entire framework. And we support a hardware template library where we have predefined modules that can be shared by applications. We support a elastic pipeline library. This is for designing hardware modules that allows you to support pipelining without having to change the entire code. And then we also have support for a direct programming interface. That's the interface that we use when we want to integrate the design with CAS. CAS, these are cycle approximate simulators that are used in architecture, or HLS. And the same direct programming interface allows you also to include existing Verilog IP, but this is kind of outside of the scope of single source here. And this is basically fed into a data flow compiler that generates a simulator and also does the code gen for ASIC. This is a simple example of a design that was written using our DSL. And this specific example is describing a matrix multiplication hardware using the DSL. The actual architecture of this hardware is basically what you see on the right side, where you have a systolic array of MAC unit. And this diagram here is the content of one single MAC unit. This block diagram here is basically the code that you see here. The way this code is structured is that you can have a user-defined type, like a performance counter, that you can just declare. You can have the description of the module port. These are the ports that you see here on this diagram. There's a describe function that basically implements the hardware block. And the matrix multiplier module here is basically this one. And you have, this is where we instantiate this historic array of MAC unit. And the framework also allows you to use the stream outputs. You can stream out any data structure directly to the console. The code that you saw previously, this is actually just a single code. I mean, this is a single header file, a single CPP file. And at the bottom of that CPP file, there is this main function. And this is the code that actually instantiate the device, the matrix multiplication device, and pass the template parameters for the object. And we basically feed simulation parameters or whatever content that we have in the application directly to the device. And then we can get the result, the output, and put it on standard out, just as if we were actually dealing with a normal C++ program. And you have also the ability to generate the traces if you need for the traditional way hardware is generally debugged. one of the challenges, one of the big challenges that we had to deal with in how to implement this is number one was how do you share types between the software and the hardware? If you create a module, how do you make the module accessible at the software side? Um, and the simple approach to this is dealing with primitive types. Primitive types in the DSL are already predefined. So it was easy for us to actually just do a static translation between the application space and then the hardware space. The application space for here for us, we call that system space. And the hardware space, we call that the logic space. And the diagram here shows how basically translation of those primitive type works. These are the primitive types that we support in the DSL. The big challenge is how do you support user-defined type? These are types that the user define that we don't have control over. So the way we approach that is we basically implement a static reflection where we have meta objects that are basically template translation that are based on the classes of user-defined types. The user-defined types are enums, structs, unions, vectors, and the idea is basically when the DSL transform the user type, it applies static reflection using the meta object and can generate the system equivalent type or the logic equivalent type. The system equivalent type is the one that the application uses, and this one is the one that the hardware uses. The extension API that is supported in the framework is implemented using UDF, which stands for user-defined functions. And this is how we actually support multi-level modeling, like functional modeling or cycle-level modeling. And you basically have to instantiate a component and just connect the component to the rest of the framework. And the interface for defining a functional model is very similar to what we use for RTL. Again, you have the concept of a structure, a concept of port, and instead of having a describe function here, it's an eval function where you actually put the implementation that you want. This specific example is just a division unit. Let's say this is a normal hardware module, but division is actually not, you decide that you want to implement your own division. So then you can create your own division module and implement it directly in a functional model. This code here is actually the code that sits in the system space. And the same thing happens also if you decide to model one of your components using cycle level modeling. Exactly the same structure, but here you can actually implement, in this specific scenario, we have a cycle level simulator for AES encryption. And the way this is consumed is also the same pretty much. The only difference is here we actually loading this object as a user-defined combinational logic, whereas here we're loading as a sequential logic. The other feature that I kind of mentioned earlier is the ability to use our module inside the HLS space. The advantage of using HLS is that we don't have to worry about implementing our own drivers and applications. And the other challenge that comes here is how do you debug? Once you nest an RTL inside HLS, how do you still debug your RTL module? So we implemented a wrapper API that allows us to nest any model that we have so that they are compatible with HLS. The framework that we're using currently is the Intel Altera OpenCL HLS framework. But this could also be extended to Xilinx or any other HLS-based framework, because usually almost all of them use C++ as the underlying language. So we have a driver that basically intercepts the RTL stop when the HLS is running. And this is how we can communicate we can create a communication between the OpenCL emulator and the Kai simulator during when we're running in simulation mode. But in actually normal execution mode, then we won't have this specific support. This was only done so that you could at least test your RTL design using a real application that is running either on OpenCL or any other HLS framework. The other advantage of using HLS is the ability to optimize HLS kernels using RTL libraries. And this is something that that is particularly interesting for those who are doing development for like CNN accelerators. Sometimes you need to accelerate a specific module in your design and then implement those modules in RTL. And you can use this framework and being able to do, again, leverage the debugging infrastructure that we support for that. The other application of the DSL, the fact that we have this uniform ecosystem that easily integrates with the software stack, is the ability to integrate the framework with CAD simulator. These are cycle approximate simulators that are used in architecture. Gen 5 SSDs are the most popular ones. And you can actually implement your design using the CAD framework, and you may be interested in doing design space exploration and using Gen 5 and leveraging the existing ecosystem of CPUs, caches, and network on chips that exist there, and being able to basically profile and test your design. And the other advantage that it also provides is you can actually directly connect the RTL implementation directly with Gen 5, which we call online RTL traces, where you can feed RTL traces directly into Gen 5 to do your simulation. On the compiler side, basically the two features, the two last features that I mentioned earlier, the software integration with HLS and the integration with Casagraph, the simulator, that necessitates that we have an RTL simulator that is really fast to be able to actually make use of that direct integration with software. So we invested quite a lot of effort into improving the quality of the compiler that is supporting this DSL. We implemented, in general, RTL simulation is 3 orders of magnitude slower and more than actual normal direct execution. And our approach has been we basically have a JIT simulator that we implemented using LMVM. And we're also doing application-specific optimization. So these are the two approaches that we use to kind of extend the performance of this compiler. On the top here, this is basically our the stages of the compiler framework, where you start with the program, with the DSL program. There's IR generation. We support dead code elimination, those standard optimization that takes place in the compiler, and we have added this new stages called proxy elimination. And after these stages, we can actually generate RG, very low RTL or fair RTL. And then this is the path that goes through the simulation. We support 2 simulators, SimJIT with this, which is our actual JIT simulator, and SimRef is the reference one. This is for systems where JIT is not supported. We have a fallback because the JIT simulator right now doesn't run on ARM, for instance. So in those situations, the simulator is the one that runs. And for the simulator, we have added 3 more stages. The standard LLVM simulation optimization are still there. This is part of the code gen. This is where we convert the data flow IR, the LLVM IR, directly to x86. So we have three more stages that we have added: sequential node coalescing, shift register optimization, and the switch table optimization. So the orange blocks are basically the addition that we have added to the compilation flow. And our approach to when I mentioned we're doing some application specific optimization. So we have annotated our IR because we have full control over our DSL. We were able to pass down into the IR more information about the data structure of the program itself. So the notion of murks, queues, delay buffers, FSM, memory blocks, this concept, this abstraction are actually accessible to the compiler. On a standard Verilog, RTS simulator, you don't have this type of abstraction. Usually dealing with the really raw primitive as registers, wires, and so on. So because we can capture this higher abstraction, we can actually implement specific optimization for those. The other thing that we have done in our RTS simulator is we don't support the X and Z states. We only support binaries 0 and 1. We made this decision because in most of the application that we have, we don't need this additional state for the signals. The compiler IR, this is a structure of what our compiler IR looks like, and you can see that we have most of the structure that are available at the DSL are also expressed here. We have the UDF, the user-defined functions, the print, the assert, the tab, the memory object, the computational object. The first optimization that I mentioned earlier, which is called proxy coalescing. A proxy node is basically a bit slicing operation, or let's say a subscript operation, or let's say a concatenation operation. These are operations that take place when you're using wires and basically combining multiple wires in the DSL. And our observation was that there was computation hidden behind the connection between proxies. And basically this optimization basically remove unnecessary proxies. And the easiest, the simple proxy that can be eliminated is the identity proxy. That basically does just basically a mem copy if you do the translation to x86, and we just get rid of this one. The next proxy that we eliminated is what we call the shadow proxy. In a scenario like in this description here, when you have two nodes that are connected, two proxies that are connected to each other, but the last one basically overlaps the previous one, the optimization, we basically only select the first one since this is the intersection of the two. The other optimization on the proxy is the adjacent proxy. We found that in some of the kernels that we implemented, specifically the ones that are dealing with encryption like AES, there were scenarios where proxies were actually did not overlap. And then when proxies did not overlap, we could have actually just combined the proxy into a single node. And often when it is combined into a single node, the single node may actually end up being actually just an identity proxy that could be eliminated directly. So this optimization actually iterates through all of the three transformation until most of the time I know it's completely ejected out of the net, out of the list. On the other end of the compilation phase, this is the cogen part. We have a stage that does the sequential node coalescing, and this one is the stage where we convert, where we basically coalesce sequential nodes based on the fact that usually the clock, the reset, and the enable signal is the same. We can actually remove unnecessary control flow during the loading of the code. And this is basically a simple illustration that shows how when you have like register R2, R3, and R3. Each of them have their own clock, and how you can actually do the merging and basically reducing the number of control flow in the final code. The other optimization is on shift registers, because the IR now that is given to the compiler has the notion of shift registers. We can do some analysis on the shift registers and then detect that actually the shift register, the maximum bit width is less than 64 bit. And we can do some analysis and actually optimize instead of generating, going with the naive implementation of a shift register in the code gen. We can either just implement it with just a standard shift operation. The same thing also, we did the same thing for switch operations. The switch operation is also available to the compiler, so we can also do the analysis to figure out that the case width of the shift register are under 64 bit. And then again, we have the same optimization similar to the previous one that can actually compress this entire switch statement into a single switch operation. A shift operation. This is a high-level overview of all of the mainstream HDL that exists today. We have classified them here into like the traditional HDL, like Verilog and VHDL. There is a new class of RTL-based HDL that are called HCL, which stand for Hardware Construction Languages. And basically this entire set here, which includes Chisel, BlueSpec, PyMTL, and we have System C as well. And then the last two ones are the HLS-based HDL, like LegUp and Special, that are directly consuming code directly from, the abstraction comes directly from C++, from a higher level abstraction. The limitation of the traditional HDL is basically just the abstraction. It's just so limited. It makes the whole design very unproductive. And this is where HLS has actually made a stride, where they have really improved the abstraction. But HLS has the challenge, they lack the support for the software integration. HLS, on the other side, you have the highest productivity. But again, I mentioned earlier, sometimes the generated code is suboptimal. And another limitation of HLS is that it is hard to really implement all hardware modules. For instance, implementing a 5-stage RISC-V processor, for instance, in HLS can be challenging. The other HDL that is really similar, I would say the ones that we inspired the design of Cache from, is System C. System C has pretty much a full software integration support, but the RTL abstraction of System C is extremely limited. So limited to the point that most development in System C is only done for the functional modeling and TML, for instance. And this is where we basically, with Cache, we have invested the time into improving the RTL abstraction by leveraging the best features of hardware construction language, and also the best features of the System C HDL. This is an evaluation of our HLS and Cache integration support. In this diagram, we basically comparing. We implemented the FFT accelerator using our framework, and we compare the exact same design with the reference implementation from Intel. This is part of the Intel SDK. We did the same thing for the Sobel filter. We basically looked at the implementation directly provided. We replicated the same implementation using the Cache framework, and we tried to compare the runtime performance of our design with the reference implementation for Intel. So the way we integrate RTL, our cache RTL with the HLS flow, we have a wrapper, we have an interface that actually wraps and manages the Avalon interface that the Intel OpenCL framework uses. And that basically we're mainly interested in seeing what was the performance overhead, or basically the difference between the two. And so we are very close to the actual same performance as the reference design. We did the same thing on the simulation side. In this specific scenario, we actually simulating, we are comparing the Intel OpenCL running in emulation mode with a kernel without any of our hardware RTL in it, versus the scenario where you have the mixed mode with the cache RTL and HLS, which is basically running on our RTL simulator. And here we are about 1.2 to 1.8 slower than the actual OpenCL emulator, which is quite impressive because we are actually simulating directly in RTL. We're not emulating the code. This is the evaluation of the compiler when we compare to all of the other state-of-the-art RTL simulators out there. The actual fastest simulator on the market right now is VeriLater. And VeriLater is able to get the speed that it does because it doesn't support the X and Z values of the signals, which is also the approach that we took here. To really maximizing the performance on the system. So we also compare it to System C, including the threading model, the multi-threaded support that System C has. We actually showed that it wasn't always an improvement for the kernels that we use. We're using AES FFT Sobel. We also had a SPMV module and also a network on chip, and also a RISC-V implementation that we did in cache. And overall, our SimJIT, which is our JIT simulator, was about 7% faster than VeriLater. And the reference implementation was 29% faster than iVerilog. The reason why we included iVerilog here is because iVerilog is an interpreted simulator. It actually run the simulation in interpreted mode, just like our SimRef. Whereas VeriLater, System C, and VCS are all compiled simulators. They actually compile directly to native code. This is the first proxy coalescing optimization that we implemented in the compiler. And here we're using the output of our HLS, and we're passing that to the other simulators, meaning that the other simulator are also benefiting from the optimization that comes from PCS. And we can see that in this specific scenario, Tango, which is our SimJIT compiler, is 1x faster in average than all of the other simulators. The coalescing node, the sequential node coalescing, was some of the, in most scenarios, we are faster. Actually, the comparison here is the baseline, you don't have coalescing supported, implemented. And this comparison doesn't include other simulators. This is just seeing the speed up of adding CNN to the the CNN stage into the compiler. And we saw the biggest performance improvement only for the Sobel filter, and if also a little bit of improvement for the FFT one. And for the shift register optimization, it's basically the same thing like this one. We turn off all of the code gen optimization and we only enable SRO to just see how much speed up we gain from just having made having turned this optimization on. And again, it shows that the sober filter is also gaining a lot. One thing to mention that is that the sober filter that we have uses a lot of registers. And this is why these two operations are actually benefiting a lot from that optimization. For the switch table optimization, the SWO, here we only enable this feature and actually try to see what's the speed up and which component. These are the components that actually mainly benefited from the switch table optimization. In the conclusion, we demonstrated the effectiveness of this uniform environment in how we can integrate the design with other applications. Ideally, the future work for this will be to see and explore the possibility of having a directive-based implementation in Clang. A little bit similar to how OpenSCC or OpenMP are implemented, where you really have the full integration with the software stack with a really solid compiler support. On the compiler side, we are interested in looking into parallelization, how we can exploit some of the high-level primitive and being able to parallelize the work on a multi-core system. This is definitely should give us a lot more performance and maybe getting us closer to how the OpenCL emulator, to the OpenCL emulator speed. Another thing that is also we want to explore is also move some of the optimization that we have here into the other tools, specifically Verilator, because this is a really popular simulator. There is also an ongoing effort. I'm not sure if you guys are aware of this. It's called a CIRCT. This is an effort into implementing Verilog support into LLVM. Basically having a compiler toolchain for HGL development. So this is also a place where we can really see how we can contribute in this specific space. And that will be all. Thank you. So if you have any questions.
All right, thanks. We have a question from Professor Andre Dehaan in the chat. Can you see the chat window? If you don't, I'll repeat the question, right? So yeah, so the main results you show were on the quality of the FPGA mapped implementation. Do you have similar results for quality of compiling to a processor from the same source?
Compiling to a processor?
Yeah, so for example, you have the single source language, right? So some piece of your computation might go to an FPGA, the rest will stay on the CPU.
Yes.
Do you have any sort of quality of runtime or whatever results for the CPU portion of your code?
This is in the context where you have HLS together, or this is just running the simulator on the CPU?
I may misunderstand your goal. You said a single source, and so one of the questions of the single source is, you'd like perhaps to do a good job in either case. So is the cache that you write when you compile it to the processor doing worse than writing good code in C or something and compiling it to the processor, or is it doing equally good? Right, and so we saw your case where you're mapping it to the FPGA, and you show that you're doing relatively well. And I'm wondering what happens when you go the other direction.
Oh, I see. So basically, writing the same FFT directly in C++, and then compiling and comparing with the FFT implemented in cache.
Yes.
Oh, I see. Yeah, we don't have. I mean, it will be very slow. I mean, out-here simulation is 3 orders of magnitude slower than actually running directly a normal C++ program. I'm assuming that this will be probably, hopefully, 2 orders of magnitude slower than actually just running the application directly instead of having to go through actual simulation.
Okay. So I guess I did, perhaps I missed or misunderstood you at the beginning.
Yeah.
I was thinking that you wanted to say the user should write it once, and then then tools or whatever, or as part of your hardware software design, you could put it on one side or the other, and it would work. It would work well. But it sounds like from that answer, you're saying that if you know it's going to run on the processor side, you should just write it in C, not write it in cache.
Yeah, this is hardware development. This is not software development.
Okay, so it's not hardware software co-design in the sense of I'm going to write this thing and then later I'm going to figure out whether it runs on the hardware side or the software side.
This is software hardware co-design in the context where I need to implement the hardware side, my hardware accelerator, and I do the development in the same environment, and I can test the design as I'm making progress. Yeah.
Okay, thank you.
So it's not the scenario where you could go either way. Yeah.
Okay. Yeah, I have one quick question. So I think you kind of mentioned that in your conclusion slide, right? So some of these optimizations that you talked about for the simulation performance improvements, they could be mirrored in Verilator or these industry standard tools.
You will need to have a really it could be, but it's not obvious how to do that because you have to implement some form of inference. You have to implement a really smart inference pass where you can just read a Verilog block and kind of infer what the intent of that code block is trying to do. A little bit the same way I mentioned that analogous to FPGA hardware blocks. On the FPGA, the compiler has a way of kind of identifying a particular code block and kind of figure out, oh, he's trying to do this. Let me just use a hardware block for this module. So you have to do something a little bit similar for Verilator to be able to do something like that. For the LNVM one, it's much easier because you have the IR. This approach is probably the one that will have the biggest success because it's a full compiler toolchain, and the input to this framework is not actually Verilog. It's actually an IR that Verilog could generate. That they have another class to create the IR. Yeah.
Got it.
That's a good question.
And sort of a allied question to that is, are there sort of some features in your development environment that could be baked into high-level synthesis, for example? Right. So could HLS tools borrow some features of what you're trying to do? Not for simulation optimization, but maybe for hardware generation, right? Try and improve the quality of the hardware generation.
The only one that I can think of is basically what I was describing, the acceleration of RTL libraries. So that's not improving HLS itself. That is basically, it's not improving the HLS compiler. It is improving your kernel in the context where some of the HLS code is redirected to RTL.
Right. Makes sense.
And the other thing from the debugging side, I was at the FPGA conference just last year, and I was told that Xilinx has added a new feature into the VTEX product suite, where they can actually now integrate RTL inside the HLS, the HLS flow. So this is basically what I'm trying to say here is that there's an ongoing effort also on the Xilinx side to also do something similar to this. Yeah. But currently, as I'm aware of the OpenCL, the Intel path doesn't have this functionality. And one thing that they definitely don't even have as well is even the path that uses the RTL library, they don't have support for simulation.
Right. Okay, we have some time for other questions from the audience. Okay, I have maybe one more, probably the
Yeah.
last one. Yeah. So you had some slide where you showed how to integrate your cache generated code into Gem 5. I was just wondering, so is it an RTL translated version that gets compiled in, or do you have some cycle accurate version that you produce that is compatible with Gem 5?
So our simulation, we have an API that is exposed by the simulator, and the API has an interface for that basically map with those CAS, those cycle accurate approximate simulator. They usually have like a step function,
Right.
and so that's the interface that actually maps into the CAS simulator, the Gem 5 or SST. But the
So
actual
one step
implementation,
is one cycle of execution in your hardware.
um, it is two step. Yes, yeah, you could say one cycle, two clock ticks.
Okay, understood. Yeah.
The on the But when it comes to the hardware itself, to the design itself, you could implement the design itself either in as a cycle accurate model or as an RGL model. That would be up to you. Yeah.
Got it. Okay, that's it from me. Are there any other questions? I don't think so. So if not, then let's thank Blaze once again. Thank you very much for presenting to our group. And yeah, I'll send you the link to the YouTube upload later today. Okay, so next week we have a speaker from Imperial College who will talk about high-level synthesis. All right, see you guys next week. Thank you.
Thank you.